Hi there, everyone. Do you remember on Friday we talked about the different sorts of turning point? We had maximums, or maxima is the official plural, and minimums or minima. And then we had these inflections, which came in two flavours, those ones or those ones. And we were differentiating to find those turning points. But what we were having to do was use our knowledge about what the graph looks like to decide what sort of turning point it is. And I want to address that today and look at how we can actually use differentiation to tell whether we're dealing with a maximum, a minimum, or an inflection. So my objective for today is determining the nature of turning points. So their nature, they could either be maximums, maxima, minimums, minima, or inflections. And here comes one of those things where I say, if you don't understand this, it doesn't really matter, but I want to try and explain why what we're doing today works. So what I want you to do is this: consider a minimum point, okay? And what I'm going to do is I'm going to consider the gradient of this minimum point as it goes from here to here. So at this, and I'm going to plot it. This is a graph of the gradient of this curve. So here I've got a steep downhill line, so that's a really steep negative gradient. And that gradient gets less and less negative, doesn't it? It becomes less and less steep as you move towards the turning point. And at the turning point, I know the gradient is 0. And then after that, it starts to get really, really steep. So it becomes really, really positive. And what you actually find is that you get a line like that if you plot the gradient. What's the gradient of that line? Well, the gradient of that line is positive. So what we find is when we have a minimum, the gradient of the gradient is positive. All right, I'm just going to write minimum. Just going to write that down just to run. Now, it's a bit hard to get your head around because we're talking about the gradient of the gradient, not the gradient of the curve itself, but the gradient of the gradient. This green line is me plotting how the gradient changes, and the gradient of that line is positive. Okay, what about with a maximum? Okay, so with a maximum, here we've got a really steep positive gradient, so the line's really steep there. So if I was plotting that on a graph of the gradient, and here it's 0 because at the turning point it's 0, and then down here it's really, really negative. So we get the reverse is true. The way the gradient of this curve changes as it passes through the maximum is it starts off really, really positive, gets smaller, becomes 0, then becomes negative. So we get that. We get a downhill line. The gradient of the gradient is negative. So I'm going to write that down. Maximum, negative. It's a little bit more confusing with inflections, and again, if this confuses you, it doesn't really matter, but because it varies. It's not a straight line with an inflection. Whereas this had a constant gradient that was always positive, and this had a constant gradient that was always negative, the key thing here is that it's the same all the time. So it's positive, less positive, becomes 0, back to positive again. So you get something that looks a bit like that. So I can't say the gradient with an inflection, the gradient of the gradient is positive, negative, but I do know that at the turning point, the gradient of the gradient is 0. Okay, so at the turning point, the gradient of the gradient was 0. At the turning point here, the gradient of the gradient, not the value of the gradient, but the gradient of the gradient was positive. That line was steep and that was negative. Okay, now if I have if that's completely lost you, then doesn't matter, because you can actually start the video from now, because what I'm going to do is show you how we can use differentiation to prove the nature of turning points, but it uses the stuff that I've just talked about. So I'm on page 276 and question 3, and we're not going to do all of these now, obviously, we're just going to do some of these now. And for the purpose of this video, I'm going to forget everything I know about the shape of graphs. So for example, I already know that this graph is going to have a maximum. Sorry, no, it's going to have a minimum, isn't it? Because it's a happy quadratic. But I'm going to ignore that fact for now. And I know that this one's going to have a maximum, and I know this is a happy cubic, so it's going to have a maximum followed by a minimum. But I'm going to forget that for now, because I want to show you how we can use differentiation to show that. So for part A, they don't use the phrase turning point, but that's what they mean, the points with a gradient of 0. I'm going to find the turning point. I know it's just one. And I'm going to then establish what sort of turning point it is using differentiation. So that's my function. I'm going to differentiate it. I get 8x plus 6. Where the turning point is, well, I ask, when does the gradient equal 0? This is from Friday's lesson, isn't it? So minus 3/4 or minus 0.75. Okay, I then, to work out the coordinates, substitute that into my original function. So I'm going to use my calculator for that. So fraction or decimal doesn't matter, minus 2.25. But can I really encourage those of you who aren't yet using your calculator for the substitution to start doing so, because you know, I know this is fairly straightforward, but you know, it's just fraught, isn't it? You know, x squared when it's negative, there's plenty of scope for mistakes. Anyway, so we know there's a turning point at this point. We know that was where the gradient was 0, and we substituted x into the original function to get our y value. But what sort of turning point is it? Now, secretly, we actually already know. We know it's a minimum, but let's pretend we don't. So it all comes back to the gradient of the gradient. So I've got here a function for the gradient. If I want to know the gradient of that, I can differentiate it again. So I'm going to differentiate that again. 8x just becomes 8 and 6 disappears. So that's nice and easy. So I know that the gradient of the gradient is 8. It's positive. It's always positive. And do you remember what we said about the gradient of the gradient? If it's positive, it means you're dealing with a minimum. So because the gradient of the gradient is positive, it means that that point is a minimum. Now, we knew that was going to happen, didn't we? We knew that was going to happen. So we've got a minimum at that point there. Now, do you remember Martin Lavelle at Plymouth saying, you know, we've got something new here, the gradient of the gradient, we've got to call it something. So if it was you or me, we'd come up with a clever name for it. Unfortunately, people have called it something already. So what we call it is, and I have no idea why it's called this, d2y by dx squared. That's what you call the result of differentiating dy by dx. And if it was f of x and the gradient therefore was f dash of x, it would be called f double dash of x. Now don't ask me why you've got d2y there and d. I don't know why. I have no idea. But there we go. It just means the second differential. All right. So that's what it's sometimes called, the second derivative or the second differential. And it is what we use to discern differential. It is what we use to discern whether or not we're dealing with a maximum, a minimum, or an inflection. I'm not going to do B, but you might want to have a go at B. B is obviously going to be a maximum, so you should find that d2y by dx squared is negative. I'll leave you to have a go at that. I'm going to jump on to C. So C, we've got, here's our function. And obviously I'm going to get two turning points here, and secretly I know one's going to be a maximum, one's going to be a minimum. So how is this going to play out? Well, sit tight and we'll see. So let's start, well, I'm going to let you do it. So let's start by firstly differentiating it and finding the two turning points. Okay, so I'm going to pause and let you do that. Okay, so 3x squared minus 2x minus 1 disappears. When does it equal 0? Well, use my equation solver and got x is 1 and x is minus a third. So I've worked out what y is by going back, don't forget, to the original function. So I've got a turning point at 1, 0. And don't forget, you can go back up and change your value there. So if I change that to minus a third, and I can press the fraction button before or after the minus, it re-evaluates it for me. So there we go, that's 32 over 27. Is that a nice? No, it's not a nice decimal at all. Okay, so I've got two turning points, and secretly I know that the first one on the x-axis is going to be, because of the shape, that's going to be my maximum and that's going to be my minimum, but let's pretend we don't know that. So let's differentiate again. So that gives me 6x minus 2. Now when I differentiated a quadratic, d2y by dx squared was a number, but now it's a cubic. I've got a letter left in there. So now I need to substitute in my two x values. So when x equals 1, d2y by dx squared, well, that will equal 6 take away 2. That will equal 4, which is positive. So remember, I know that when the gradient of the gradient is positive, I'm dealing with a minimum. So when x is 1, that's a minimum. And we already knew that, didn't we? We'd already said that. What about when x is minus a third? So 6 times minus a third is minus 2. Minus 2 take away 4 is minus 4, which is negative. So we are dealing with a maximum. And we knew that already, but we've confirmed it. And actually, it's a bit like those discriminant questions. We're not worried about the actual value here. All we just need to know is whether it's positive or negative. So, you don't actually have to evaluate that. You just need to work out whether it is positive or negative. So shall we just summarize the results? So when dy by dx squared is positive, when the gradient of the gradient is positive, you're dealing with a minimum. When the gradient of the gradient is negative, you're dealing with a maximum. And if it's 0, which we haven't come across yet, that's when you get an inflection. And I'm using d2y by dx squared, but don't forget you've got the f double dash of x notation as well, which means the same thing. Okay? Now you may choose to do D. Don't forget to multiply this out. Don't try and differentiate until you've got terms that are added or subtracted. So we would multiply that out. You'd get x cubed minus 4x squared minus 3x. So it's another cubic. You'd get two turning points, and you could use the process to work out whether they are maxima or minima. I'm going to move on though to a couple of more interesting questions. So we're going to have a look at E and G, because to be honest with you, I'm not really sure what this graph looks like. So let's have a go, shall we? So E, here's my function, but I'm not going to write it like that because I know I'm going to be differentiating here. I'm going to write it in index form. So there we go. So I'll just move that up there now. So I've rewritten E in index form. So I'm going to differentiate it. So x becomes 1, and that becomes, so you multiply by the power, so that's minus 1x, reduce the power by 2. And I want to know when that equals 0. Now this is where it is useful, well, I'd say essential, to actually understand what that means. So this takes us right back to the things we did in the first lockdown during those summer lessons, where I reminded you that x to the power of minus 2 means x squared. So when does it equal 0? Well, you know how I feel about fractions by now, and you also know that 0 is your friend, so I'm going to multiply everything by x squared. So that will give me 1 times x squared there, kills the fraction. 0 is still 0, good old 0. And, well, I've got 3 or 4 ways of doing it. I could reach for my calculator. A is 1, B is 0, C is minus 1. You might have already spotted this is a difference of 2 squares. Or you might have just said, okay, x squared equals 1. So whichever way you do it, you get plus or minus 1 as your answer. And if I go back to my original function, it might help me to look here. And again, I would strongly recommend you use your calculator to substitute it in and work out the y values. So when x is minus 1, you'd get minus 1, and 1 divided by minus 1 is minus 1, so that would be minus 2. Sorry, I know you can't see that, but there you go. And when x is plus 1, you get 1 plus 1 over 1 is 1, so you get y is 2. But use your calculator, not a problem. Minus 1 minus 2 then is 1 turning point, and 1, 2 is the other turning point. Okay, what about the nature of those turning points? Let's work out d2y by dx squared. So my constant disappears. This term here, multiply by the power, so it's minus 1 times minus 2 just becomes 2. Reduce the power by 1, which means the same as, okay, so substitute in your 2x values. What do you get when x is minus 1? What do you get when x is plus 1? And tell me whether these are maximum, minimums, or inflections. Okay, so when x is minus 1, this evaluates to be minus 2, which is negative, so it's a maximum, so that point is a maximum. And similarly, when x is plus 1, it's positive, which is a minimum, so you get that. It's really important that you clearly annotate the work as you go. So, and by that I mean, make sure that you label this as d2y by dx squared. So, I've differentiated here. So this is my original function. This is my differential. This is my second differential. And I know I use colour change to help pick it out, but it's important that it doesn't all get lost in a big sea of algebra. Now, what if you're not happy? What if you don't think you've got it right? Is there a way of checking? Well, if you went to a rubbish school that doesn't give you a calculator like this, there isn't a way of checking, but we have a way of checking because we can actually plot the graph of these functions, and the graph will show us the turning points as well. So I'm going to type in this function. I'm actually going to type it in as it was in the question. So it was x plus 1 over x. Now you may remember when we type in functions that you sometimes have to fiddle with the axes. So I forget how I've got my axes set. Actually, they're not too bad, are they? But don't forget you've got v window is the way, and actually starting with standard is a good way of doing that. So if you go exit and then you have to draw it again. Yeah. So actually, look, I've got two fairly clear turning points there, one of which is a maximum, one of which is a minimum. So that sort of looks right, but gets even better because my favourite button on the calculator, the G solve button, It has a max and a min function. So let's press the max button. There we go. It's identified a maximum when x is -1 and y is -2. Bingo. And let's press exit. Oh, gsolve. I think I could have just pressed gsolve again there. What about the minimum? There we go. It's identified there's a minimum when x is 1 and y is 2. Bingo. So it is impossible to get these questions wrong because you've got a graphical calculator that will confirm you've got it correct. Your answer, can't you? Good stuff. Right, so I would like you to have a go at F as your submission question, and I look forward to seeing how you get on with that one. Take care.